Alright everyone, in this second video we're going to look at the three-dimensional version of the Voronoi cell algorithm, and the extension of basically looking at, let's say, for example, this project by SoftLab in New York, and this installation project by Andrew Cudless done at Ohio State University. And the sort of basic setup, not exactly for these, although I will eventually post a definition that replicates seawall in particular, but those sort of basic principles. And so same thing, going into the mesh tab under triangulation and pulling out the three-dimensional Voronoi cell component. And same thing, it asks us for points and then asks for a optional diagram boundary. Same thing, it's just, it's three-dimensional. Okay, so these points, I'm going to actually try to generate these automatically instead of putting in points manually. Obviously you can do that. So under the vector tab, grid, there will be a couple populate, components. So take a look at these really quick. Populate 2D, populate 3D, populate geometry. And these are just like random population sort of components. This first one needs a rectangle, right? So similar to the one before. It just, fills a 2D plane with points. So this is nothing, kind of super special. The two, probably in this case, we're going to look at are these two. And the one thing I kind of want to point out, like one is like populate 3D, which requires a box, right? So a sort of box as this sort of boundary diagram as an input to be able to populate a 3D region. And this one, populate geometry, okay? And they actually operate slightly differently, at least in the sense that if I, with populate geometry, this can be actually anything. Geometry to populate curves, surfaces, B-rips, and meshes, right? So when I hover of it. So let me actually just grab from geometry a geometry sort of tab in here. And to kind of make the point, right, if it's a curve geometry, if I right click, set one geometry, and I'm picking this curve, then you'll see it basically populates it on the geometry specifically, right, on the line, right, on the curve. And this file is actually the 3D Voronoi example file that you'll have on the Canvas website to download. So yeah, it's explicitly on the line, it doesn't do anything inside, right? Same thing if I switch it to this plane. Then all these points, random points, get populated on the plane, right, at different locations. And same thing if I switch it to this, right? This is a poly surface, closed poly surface. Set one geometry, right? So same thing, but in particular, I want you to notice that like it only populates it on the surface of this geometry and not inside, not in the interior. If I hide it, right? There's nothing sort of in the middle of the volume. Okay, everything's on the surface of the volume, right? So that's just like an important thing to kind of realize, that with this component, using it this way, this is what happens. Okay, now I'm going to start with this, except eventually we'll move to a sort of approach that more kind of approximates that, right? So we can give these points, and you'll see essentially over here, right, the Voronoi 3D component has basically kind of done all the subdivisions. And let me sort of like, let's hide these things, hide it, just so it's out of the way. So you'll see I'm getting this sort of diagram, and let's bake it just to see. Okay, what you're getting. And I'll switch my mode to shaded just so it's a little bit clearer. Now, because of what I said earlier, that these points um, are all on the surface of that original sort of shape, right? That original geometry, this geometry shape. Um, Sometimes, essentially, like what happens is that the Voronoi diagram tends to be kind of split in two, or if basically like any of these shapes that I'm selecting here, for the most part, they're kind of like on the surface or very close to the surface, and there's less sort of interior cells, like if you will. So if I do a sort of like crossing selection like this and just basically barely grazing the boundary of this, you can see this is actually roughly, half of all the cells in here. This is roughly the other half of the cells, right? If I actually deleted these guys, I would be basically left with all these. And you can kind of tell like all of these and all of these, because they are adjacent to like one of the original sort of sides of the boundary containment. Um, there's actually no interior cells, right? Which is, at least in the case of this, right? In case of this project, these were all kind of interior cells, right? Which means that we need to find a way to actually kind of get more interiorized cells instead of having all of our points be on kind of like the surface of the shape. Okay, so that's just like something to notice or understand, kind of as we go forward. But besides that, right, how do I get from here, which is kind of like a square, boundary containment, to here, right? In the sense that like, okay, we're going to try to carve out the shape that we want within this sort of 3D cellular structure. And that kind of actually brings us back a little bit to the principles of the geometry and approach of the water cube, right, as a sort of big Booleaned out volume. So in this case, I need to get back my, whoops, sort of house-shaped volume, okay? And basically what we're going to do, we're going to take the output of the Voronoi cell and then basically do a Boolean union sort of logic on it. So in here under intersect, under shape, we'll do solid intersection, right? So basically only, and you can look at the icon, right? It only retains the sort of crossing of a Venn diagram in that sense. Okay? So just two operators, right? So one of the operators is actually going to be this, right? Because this is the geometry that we linked in. Okay, and so with the solid intersection component, one thing that I do know is that you typically actually want to put the cells in the input for A first for it to work correctly, and then the geometry, that's typically the second operator, or in the B slot. Sometimes it just won't work the other way around. So just kind of be mindful of that. And so let me hide this and the original. So what we're getting now is the sort of intersection between the Voronoi cells and our input geometry, and you get basically the combination of both. Now one thing you'll note is actually you get this like kind of like sort of short cutoff on the sides compared to the original geometry, and this is actually due to the fact like you get these little, it's not exactly accurate. Let me hide this. And this is primarily actually due to the fact that the Voronoi cell diagram actually only looks at the points, right, and not the geometry. And so when we're populating the geometry, it doesn't necessarily populate at the very edges of the geometry, right? And so the boundary of the Voronoi diagram actually kind of cuts the geometry off at some points, especially at the tip here, right there, right? So if you're unlucky enough that, like, when you're kind of changing, let me close that off, when you're kind of changing either the number of points or the random seed, that sort of thing, your sort of overall boundary will change. So let's look at that effect really quick. put in a slider and let me do like maybe a lot less number, and I make it less and less. You'll see that the sort of size of this automatically generated boundary changes, and sometimes it actually shrinks much more than the sort of size of the geometry, because there's no points there, right? And so the populate geometry, the Voronoi diagram doesn't know that, that you have to kind of push to that edge, right? So basically, and we can do a slider for the seed as well. If we don't have 3 points, then that's going to be the sort of weird boundary thing that you get, and just, it's not very, accurate, right? And so the workaround for that is really actually just to kind of do a bounding box on your initial input geometry. So we'll put a bounding box component here, just to kind of force the populate geometry to use, or the Voronoi diagram to kind of use this bounding box as the sort of outer diagram, right? So this will force it to actually enclose all edges of your original input geometry, regardless of whether or not populate geometry populate where the points are located. So if I close this, then you'll see, regardless of like what seed I make, or even how many points I make, this sort of outer containment boundary will not change. Okay, so you have to use something like this to kind of force it to cover all of your input geometry. And with that, then you would get this. And this is a slightly different number or seed probably, but in this case. And if I kind of up this count to something a little bit higher, but the point I was making was that essentially, even with this and that many points, like every single cell or every single sort of volumetric cell here is still bounded to an edge or a surface, original surface. And so if we wanted like basically more interiorized cells, we can't use the populate geometry version, right? And that's why you kind of replace it with the populate 3D version. And so in that case, what we do, everything else is basically, let me delete this. Everything else is basically identical. This actually, no, we're taking it from here. So we would take it from the sort of bounding box of it. Number's the same, and we can kind of make the seed the same as well, right? And copy paste this over, swap it out. Okay. And this is the same except for this input. All right, let me hide that. And with this one, what you'll see is that because populate 3D actually does make points that are inside the volume or within the volume, actually use in the Voronoi 3D sort of component itself, it does has a list that you can pull and connect a panel to, and it will tell you whether or not that cell is part of the original boundary or the original outer boundary. And so everything's true, but you have a couple that are false, right? And so those would be cells that are more interiorized in sort of relationship, not necessarily to this like outer, house shape, but the original outer, let's say, Voronoi cell here. Not this one, but this one. Yeah, and you're actually kind of able to call that out or pull that out by using the call component or call pattern, which takes all those cells as a list input, and then using this, which is basically a true-false pattern, to kind of find basically essentially the ones that are either true or false. And in this case, it's saving the ones that are true, which are the ones that are on the exterior. But I don't want that. I want I want the ones that are on the interior. So I can basically come here in the calling pattern and just like invert it. And so it leaves me with essentially the cells that are all interiorized, right, on the inside of this. And so if you kind of compare these two diagrams, you see that what I have now, whether it's like reversed or highlighted in green, but this outer containment boundary is all in green, and all the cells that are interiorized or interior cells are in red. So you're able to tell that, okay, all of these were generated from like interior points, right? Not points that were on the surface. Okay, so typically from there, then you can kind of decide what you want to do. Like for example, with these guys, um, if you're kind of trying to replicate, let's say, this project to a certain degree, then you can obviously see that, okay, there are parts of it that have a frame around it, and you probably need to get some like offset fillets, basically the same way that we saw it earlier in the 2D version, except you would be doing this in 3D instead. So very simply, let's say if we're taking this guy here, and let's try to separate these two different versions. So these are kind of shared. This is the Populated D version, Populate 3D version. Okay. So something like this, obviously these are sort of like three-dimensional cells. It's cell outputs, right? Closed B-reps. So you can, our good buddy, deconstruct B-rep here to get access to the faces, each edge, and the vertices, right? And they're kind of organized in cells, right? In particular. These are, some of these cells have like many faces. So you'll see that some of these cells have, 14, 15 faces. So it just depends on how complex those faces are, right? And you can kind of get it down to the component levels essentially, and edges, right? And so these are kind of organized by edges with a cell, not in a face. That's why sometimes you'll see if I'm trying to get to the face, and I'm trying to get to the edges of a particular face, I'll actually put two of these in succession, right? Which means I'm getting essentially all the faces, all the trim surfaces in one cell, and I'm looking at all the faces in that one cell to get to, let's say, all the edges in each face, right? In this case, I'm looking at the overall B-reps, right? I'm grabbing all the faces. The faces are actually kind of organized, in this case, by cell, right? So I'm getting the faces and looking at the faces themselves individually. That's why there's like two of these sort of in succession. So I can get it to a point where, at least in this case, I'm actually trying to grab. If I'm looking at the faces, these are individual faces, right? Inside each cell. In this case, I'm trying to get to all the edges that are on each face of the cell, right? And that's why sometimes you'll see like two of these deconstruct B-rep components, like one right after the other, is because I'm trying to get down to like the component level of each cell. Once I'm here, I can then do a B-rep edges right here, like this, and get to, get to the edges of each face. And these are all kind of like the naked edge curves right here of each face, right? That then actually will allow me to, let's say either fill it or kind of, actually in this case, let's join all the curves together. Once we're here, there are probably a couple of things we can do. I can try, for example, filleting it with, let's say, 0 smaller than 3.00 and see what we get. So you'll see, okay, I'm getting these sort of rounded corner faces right here. We can scale it, you know. We need a area component here that is coming from the centroids. Centroids as the center of scaling. Scaling factor between 0 and 1. So if you're looking at this, then you'll see, okay, so I'm able to go from the edges and take those edges to manipulate them and then kind of control the scaling factor right there. Okay, so I'm gonna try. Let me see what happens. Let's make a boundary surface from here. This is a call. Simplify it, and let's see. Close, hide all this. Okay, so this is actually the reverse of actually what I want. I actually want these guys and adding in these guys. There you go. Okay, so this is what it should look like. Basically these are our sort of joined original edge curves, and then these are the curves, the inner curves that we've done after scaling, and then we're just kind of making planar surfaces out of them, right? So you'll see that, you know, the scaling factor, you kind of make it larger, smaller, to get more, let's say, meat in this this sort of frame, just basically just like this, right? Okay, so that actually is kind of more or less the basic logic behind you know, both this project and this project. And I will post a different example because there are actually, you know, different approaches to this, but you guys can kind of take a look. And that there is also one that will kind of join these faces back in them, so you can actually do or automate the unrolling for this. So all your faces get unrolled as cellular components. All right.